All right, today we'll do section 3.6. We already kind of dipped our toe in this before we decided that that first test was going to cover sections 3.1 through 3.5. We did, however, discuss these derivative rules that were part of 3.6 that I just want to remind you guys of. So the derivative of a log is 1 over x times the natural log of b, the base of the logarithm. So if it's a natural log, the base of a natural log is e. And what's the natural log of e? Just one, right? So that just gonzos. Okay. Let's just do some derivative examples to practice using these rules. Okay, so here we have y equals the natural log of x cubed plus 1. What do we notice is going on here? Chain rule, very good. The outside function is? And the inside function is? Great. So the derivative of the outside is going to be 1 over the inside function times the derivative of the inside function, which would be 3x squared. And we'd probably just write that as the fraction 3x squared over x cubed plus 1. Feel pretty good there? Okay. What if we have the natural log of sine x? What do you see here? Another chain rule. The outside is? So when I differentiate the outside, I have 1 over the inside times the derivative of the inside, which is cosine. So if I multiply those together, I have cosine x over sine x, which is cotangent. That's our best answer. Good trig memory. If there's anybody that you can count on to have it memorized, it's Blake, Mr. Country Capitals, and the fountain of useless information. It's not useless completely, but it's like, oh, this is
it's useless.
Yeah. Maybe let's call it trivial information.
Yeah.
We'll call it trivial information. There's a use for it, but it's mostly trivial. Okay. Let's say we have the square root of natural log of x. What do we see when we look at this? Chain rule. What's the outside? The square root of x. So probably the way to think about this would be to change it to natural log to the 1/2 power. When I do the derivative of the outside, we get 1/2 the inside to the negative 1/2, and then times the derivative of the inside, which is 1 over x. So if I write this out, what do I have? I have 2x square root ln x all under 1 Everybody okay with that? So far, everything seemed pretty good. Not a big deal, right? Oops, I gotta write something here. If I look at this one, what do we see here?
Chain rule motion.
Yeah, and then another chain rule, right?
Oh,
With the square root. Yeah, yuck. What Mr. Kulik sees here? I just see two easy chain rules. So one thing that we need to kind of remember from Algebra 2 that can be quite helpful here is our property of logs. So we had a quotient property that says the log of a quotient can be written as the difference of the two logs. And the product, the log of the product, can be the sum of the logs. And the power, the log of a power, would be the coefficient times the log. So remember, what we'll be using these for is to expand. Typically the order that we want to go when expanding is quotient, product, power, unless we have a parenthesis indicating to us that we need to go in a different order. But that's the typical order for expanding. So that's what I would start with in this problem. So I notice there is a quotient, so I'll write that as log of the numerator minus log of the denominator.
What was the order again?
Quotient, product, power. Now I don't see any products here, right? There's no multiplication going on. But I do see a power, so I can use that power property. Notice I haven't done any calculus yet. Everything that I've done so far is in Algebra 1 or Algebra 2 skill. And now I'm ready to do my calculus. But look at what's happened. Look at the derivatives that I now need to take. So much easier. So much easier. So the derivative of log of x plus 1 is a chain rule. So the derivative of the outside, so that's going to be 1 over the inside times the natural log of 10. Very good. The base for log, if there's no base written, is considered to be 10. And then this times the derivative of the inside, which is 1. Okay. And then the same idea over here. And this is one that I wouldn't muck around with trying to simplify. I mean, you could add the fractions or whatever, but you need to make a common denominator. Nothing's going to be like the numerators aren't going to add together very nicely. I think it's just going to be pretty messy. I would just leave it the way it is. I don't have warm feelings about it.
Was the natural log of 10 about to be like a rational number?
No, kooky decimal. The only thing that the natural log is going to give you a rational number for are powers of e.
Okay.
And 10 is obviously not a power of e. Well, not a rational numbered power b, right?
Yeah.
Like I can write e to the ln 10, and that's a
Yeah.
10 as a power, or 10 equals, but like, get out of here. That's not helpful. All right. So that's like doing derivatives with logs in it. No big deal, right? They're all just kind of chain rule problems. And if the chain rule looks really nasty, ask yourself, is there a property of logs that I can use to make the chain rule easier to do? In particular, if I have like a quotient inside of a chain rule, it's a good candidate. Everybody's cool? All right. Here's a question for you. What if I want the derivative of the natural log of the absolute value of x?
It's just one of the rows.
Okay, why? We have the absolute value in there.
Because the memorization chart said it was that.
Good, okay. So let's show you why.
What did you say? The memorization chart said it was one of the rows. So
Okay.
it's one of the rows. Gotcha. Yeah.
So recall back to algebra 1. What's the definition for the absolute value of x? The piecewise definition?
So x is less than.
Just going to stay x if it's positive or 0. And then if it's negative, we negate it. Right? Everybody's okay with that? If I do the absolute value of -2, that would mean that I take the negative of -2, which is positive, which is what we needed to do, right? So if I want the natural log of the absolute value of x, and I want to write that as a piecewise function, I can write this as the natural log of x over the natural log of -x. Oh, not over, but that's my second piece. Everybody okay there? One little problem with what I've written has to do with the domains of logarithms.
Oh, yeah. Log equals 0.
Yeah, so just make it, has to make it greater than 0. Not a big deal. Okay. So if I then do the derivative of this, I'm going to take the derivative of the natural log, which is over x. And then I'll do the derivative of natural log of -x, which is, it's a chain rule, right? So it's going to be 1 over the inside times the derivative of the inside. And what do we notice here? Cancel out. So this is just going to equal 1 over x. Okay. This is worth remembering. I've seen on the AP exam absolute value stuff crop up in kind of unexpected or difficult to handle ways. Remembering that piecewise definition could often be quite helpful. If you run into those situations. One last topic in section 3.6 here. And that topic is about, or is called logarithmic differentiation. So what logarithmic differentiation is, it's a trick where I can make certain derivative, or make the calculus part for certain kind of derivative problems easier, but often at the sacrifice of making the cleanup algebra at the end a little bit more difficult. But you catch the right problem, and it's a very good option. And for certain kinds of problems, we'll look at one of those kind of examples here in a minute, it's really the only way to proceed. So if I look at this, what do you guys see here? There's a lot going on, right? Got a quotient, got a product, got two chains, got a whole lot of calculus, a whole lot of messy calculus. What I see is this would be something that is an excellent candidate for logarithmic differentiation, because the chain rules that are going on are just power rules, right? I have an x to the fifth and I have an x to the 1/2. Those are the situations that make excellent candidates to use logarithmic differentiation on. Or something that has no other chain rules, that's just products and quotients, right? That's pretty good too. So the first step is to take the natural log of both sides. I'm then going to use my properties of logarithms. So I'll begin with the quotient property. So now I can rewrite this as the numerator, or log of the numerator minus log of the denominator. I'll then use the product property inside the first logarithm to rewrite that as log of the first factor plus log of the second factor. And then I'm going to use the power property to move those exponents to coefficients. Worth pointing out here that I've yet to do any calculus. This is all like Algebra 2 level stuff that I've done to this point. But now I've got this thing fully expanded out. Now I'm ready to do the calculus, so I'm going to take the derivative of both sides. What do I get when I take the derivative of natural log of y? 1 over y dy dx. Remember, this is like an implicit differentiation situation. Since the derivative is with respect to x, if I'm differentiating a variable other than x, it creates one of these differential terms. Okay, and then if I take the derivative of 3/4 natural log of x, I can pull the 3/4 out. And then the derivative of natural log of x is just 1 over x. And then if I take the derivative of 1/2 natural log of x squared plus 1, I can pull the x squared out. The derivative of the natural log of x squared plus 1 is a chain rule. So that's going to be 1 over the inside times derivative of the outside. And then the same thing on the last one. And pull out the -5. Derivative of the outside is going to be 1 over derivative of the inside times derivative of the inside. Is everybody okay with what I did there? The calculus is now done. We just have some cleanup to do. But that was a heck of a lot nicer than what the alternative was looking like, right? we would probably still be writing out our setup, dealing with all the quotient and chains and products and everything else going on inside of that beefy boy there. Okay, but we're not done. What still needs to happen? What are we trying to find in this problem? We want the derivative. We need to get that dy dx by itself. So we need to still multiply both sides by y. Now, when I do that, I'm not going to write y in terms of y. I want to write y in terms of x, because the rest of my derivative is written in terms of x's. How do I write y in terms of x? Just the original problem. Now, if I was really trying to simplify this, what would I still need to do? Well, I would start inside here, making a common denominator, right? And then adding all the numerators up, or subtracting, I guess. One of them is a subtraction problem. And then I would worry about the distributing, and it's going to get pretty messy pretty quick, we can see, right? So the downside here for the logarithmic differentiation, if this is a show problem where I tell you what the answer needs to be formatted like, you may have some pretty nasty algebra to clean up at the end. Maybe not a great candidate for those kinds of problems. Not saying that it's wrong, it's not, but the algebra might be worse than the calculus, right? And we've seen that happen, right? That oftentimes the hard part is the cleanup at the end and not so much the calculus in the beginning. But for this problem, I would say, let's just stop here, right? And I'm going to point out to you the hassle, and then we're not going to spend 10 minutes like grinding through that, because we can't get those 10 minutes back after we start, right? I want to look at another example. One that is really intractable for us to do any way other than with logarithmic differentiation. If I look at this function, x to the square root x, is this exponential? No, because the base of the exponential is a variable, not a constant. Is it a polynomial? No, because the exponent of it is a variable, not a constant. Do we have a rule to deal with a function like this that's neither exponential nor polynomial? No. What are we going to do? Logarithmic differentiation. Okay? When you see something like this where you have variables in both the base and the exponent, that is the route that we're going to need to take. Okay? So just like before, I'll take the log of both sides. I'll apply the power property of logarithms to move that exponent to a coefficient. And now I'm ready to differentiate. When I go to take the derivative here, is there any problem? No, I have a nice product property, but two easy things to do the product property with. That's no problem. You guys cool? What looked like a really kind of impossible problem is starting to look like a pretty doable one, right? Now the square root of x, if I take the derivative of that, 1/2 x to the negative 1/2, and then the derivative of natural log x is 1/x. Use the product property there, right? Because those are two things multiplied together. Any questions so far? Okay, well, let's try to clean this up a little bit before we multiply the 1/y over. So when I do that, I'm going to have natural log of x over 2 square root x. Everybody agree? On cleaning up that first piece. What do I get when I multiply x times 1/x? I would think about this, the x in the denominator there as 1 square root x. So when I multiply, I just get 1 the square root of x. You guys cool with that? Now, that's a little bit sneaky. If you didn't notice that, it wouldn't like impede you from doing the problem, but it makes making the common denominator a little bit more of a hassle, and you end up like redoing work that you would have already undone in a you know what I mean? Yeah, doesn't really matter. So make my common denominator, and we get natural log of x plus 2 over 2 root x. But are we done? No, why not? Got to multiply by y over. But in this case, is that a big deal? No, man. And that's probably as good as we can do. I mean, if you really wanted to get picky, we could probably combine the x to the square root x and then the dividing by square root x. If we really wanted to, but like, I don't think that's a big deal. Now you're just shuffling deck chairs on the Titanic kind of thing. It's like a matter of taste. Alexis? Sure. What do you guys think? Pretty relatively easy section if you know your derivative rules, which we've worked really hard on, I think, the last week or two to get much better at. This should have felt pretty smooth. Nothing sneaky, or terribly sneaky anyways. That's it for this section. It's just going to be practicing those couple of skills. So that first block of problems is just derivatives with logs in it. The second block is problems is logarithmic differentiation problems, but should be pretty doable. That'll close section 3.6 for us. We're also going to do section 3.7 today. So section 3.7 and sections 3.8 contain no new ideas. It's just going to be taking the things that we've studied so far and applying them to context. Okay? The actual calculus that you'll do in these sections in 3.7 and 3.8 is going to be really, really easy. The difficult part is going to be like figuring out where to apply the calculus. The actual calculus you do will be quite easy, though. The title of 3.7 is Rates of Change in the Natural and Social Sciences. So we'll do a couple of examples here from this this section. I put in a whole bunch of examples. We probably won't do them all. The first one we're definitely doing because this is like a super canonical AP kind of level question. So it says the position of a particle is given by the equation S equals f of t, which is equal to t cubed minus 6t squared plus 9t, where t is measured in seconds and s is measured in meters. Find the velocity at time t. Well, this sounds very much like a chapter 2 question, doesn't it? We did a lot of stuff pretty similar to this. What's the relationship between velocity and position?
Velocity is the derivative.
Great. Velocity is the first derivative of position. So that means it's going to be 3t squared minus 12t plus 9. Well, that's it for part A. Mr. Kulik. It is what it is, guys. It is what it is. Part B asks, what is the velocity after... Oops, I don't mean V prime. I meant just V. Excuse me. What is the velocity after 2 seconds and after 4 seconds? What am I doing there? Just plug in 2 in for t into my derivative that I just found. Let's see, what's that? That's going to be 12 minus 24 plus 3 is negative 3. Or plus 9, I meant. And v of 4, that's going to be 3 times 16. So that's 48 minus 48 plus 9. Well, that's just 9. That was easy as well. No big deal there, right? Part C says, when is the particle at rest? What does at rest mean there? Velocity should be 0. Okay. So I'm going to just be solving then. 3t squared minus 12t plus 9 equal to 0. What kind of an equation is that? Quadratic. Very good. To solve a quadratic equation, what are some of the possible techniques I might use? Quadratic formula. Factoring are the primary 2 that I would use. Since I'm doing this mostly by hand, I would try factoring. I noticed that if I look at the coefficients, they're all divisible by 3. So I would probably start there. And now to factor this, it's much easier since the leading coefficient is now 1. That was enormously helpful. 2 things that multiply to give me positive 3 and add to give me negative 4 are? Negative 3 and negative 1. Very good. So that tells me at time, at 3 seconds and at 1 second, my particle is stopped or not moving. So far, so good. Okay. It says in part D, when is the particle moving forward? That is, when is it moving in the positive direction? What are we doing there? When is the particle moving in the positive direction? What am I trying to find? When the velocity is positive. Okay. Remember that the velocity in this case was equivalent to this When I multiply two things together, in this case t minus 3 and t minus 1 are the two things that I'm multiplying together, when can I get a positive number? I multiply two things together. When will I get a positive result when I multiply them together? What do those two things have to be? They both have to be positive, or they both have to be negative. Cool there. So I solve that. I get when t is greater than 3 and when t is greater than 1. Well, hold on a second. T is greater than 3 and t is greater than 1. What is that really the same as? Yeah, it's just the same thing as t is greater than 3, right? Oh, we'll hold on to that maybe for a second. If I go over here, t is less than 3 and t is less than 1. Well, really, what's that the same as? Yeah, just the same thing as t is less than 1, right? If you're less than 1 and you're less than 3, the less than 3 part doesn't really matter. Okay, so if I were to write this as an interval, I would say from 3 to positive infinity, we're moving forward. But over here, I wouldn't say from negative infinity to 1. Why not? What is t representing? Time. So what should the lower bound be on time? 0, and it should be a bracket rather than a parenthesis. Everybody's okay with that? We're just being picky now, but like context matters because we're now working on a story problem, not just like some arbitrary equation. It has meaning, so we have to be a little bit careful to use our noggins about stuff like that. Okay. Part E says then to draw a diagram to represent the motion of the particle. Okay. Well, since this is just talking about a particle moving in a direction, I'm just going to do this as like a two-dimensional piece. So there's my value for S. Now, there are a couple values that I care about, right? What times am I inherently going to have to worry about when I'm doing this drawing? 3 and 1 and one other. 0. Everybody okay there? For each of these, I'm going to calculate the position of the function. So I know when I'm drawing my position diagram here, where to kind of put that point. Okay? So I'll go back. How do I calculate S? I use the formula from the beginning. When I plug 0 in, what do I get? 0. When I plug 1 in, what am I going to get? About 4. 1 minus 6 plus 9. When I plug 3 in, 27 minus 54 plus 27. 0. You guys would have used your calculator. It's not a big deal. Okay, reminder that we're going forward from 0 to 1. It's going to be backward from 1 to 3, and then forward again from 3 on. Okay. So we're going forward here, and this is time 1, position 4. We then turn around and we go backwards to here. That a little bit neater. It really wasn't any neater. This is time 3, position 0. And then we continue forward after that. I guess I should label this point down here. Is everybody okay with how I drew that diagram? Okay. Not a big deal there, right? Part F says, find the total distance traveled by the particle during the first 5 seconds. Now this you have to be a little bit careful about, because the natural intention would be, I'm just going to do s of 5 minus s of 0, right? The problem is s of 5 is going to be like over here somewhere, and it's not going to count the whole path. So what we need is to find the forward pieces and the backwards pieces separately. Yes, sir. Certainly. So the forward parts, we have one forward segment there, and then one forward segment there. Everybody agree? So the first forward segment goes from 0 to 1, and the second forward segment goes from 3 to 5. Everybody's good with that? Okay. So I'm going to take s of 1 minus s of 0. Well, I already know s of 1 is 4 and s of 0 is 0, so that's 4. Distance 2 is going to be s of 5 minus s of 3. Well, s of 3 we already know is 0. We calculated that before. Let's go back and calculate s of 5 now. How do I do that? All the way back to the position function given to me in the problem. When I plug 5 in, I get 125 minus 150 plus 45. That gives me 20. You could certainly use your calculator to do that. I guess these are meters, right? I think they told me that S was measured in meters. And then we're moving backwards from 1 to 3. And those we both already calculated. So my total here is going to be just the sum of those 3 calculations, which is 28 meters. Everybody cool with that? Again, nothing super duper complicated there, but you have to think about what's going on. Make sure that you're counting the forwards and backwards pieces separately. Part G then says find the acceleration at time t after 4 seconds. Great. So I know the acceleration is the second derivative of position or the first derivative of velocity. That's probably where I would think about it from. So if I go back to my velocity function, the derivative of 3t squared minus 12t plus 9, 6t minus 12. Everybody agree with that? Easy enough. So after 4 seconds, I just plug 4 in. I get 12 meters per second squared. Everybody cool with that? When I screen capped this problem from the text, I missed 2 parts of because they ran on to the next page and I didn't notice. There's 2 more parts. Part H says just to graph the position, velocity, and acceleration functions on the interval from 0 to 5. How am I going to do that? Type them into my calculator, which I've already done. Set my window from x0 to 5. And then for the acceleration, I know at 4 it was already 12, so I just picked an upper bound of 20 and kept the lower bound at negative 10, just hoping that was probably enough. I know that there's going to be some negative velocity. It'll probably be fine. And if I hit graph, oops, I turned off position for some reason. So this one is my position function, the one that looks cubic. The parabola is my velocity function, and the straight line is my acceleration function. Everybody's okay with that? So that's H. I'm just going to write on the calculator because I'm not redrawing that thing, right? And you guys with the nice color-coded calculators, that's even easier because you can color-code the stuff and it comes out much nicer than the little black and whitey or green and black one that I got. And the last part says, when is the particle speeding up and when is it slowing down? Well, first we should talk about like what we're going to be looking for on the graph, right? So speeding up.
The acceleration, that's a positive.
Well, acceleration needs to be positive and the velocity needs to be positive, right? Because if your acceleration is positive, but your velocity is negative, what are we doing? Yeah. Okay. What's the other situation we might be speeding up?
Acceleration also.
Yes. Good. And that's just we're speeding up in the reverse direction, right? So then obviously this one is acceleration negative, but velocity positive. Okay. Now I would say that we've identified what we're looking for on our graph. Now let's go and look at the graph. But yeah, you're dead on. We're just going to use the graph to do this. All right. So I'm going to go back and turn off the position function because that's just in our way. We don't need that. So let's look for this case first, acceleration positive and velocity positive. That happens like starting here at this x value, correct? What's that x value at? 3, because that's one of the places where velocity starts to be, 0. Velocity was 0 at 3. That was the furthest one to the right. So 3 forward. Everybody agree with that? Okay. Let's find the place now where both are negative. Where does that happen at? Sure. Right, starting here and ending there.
Wait, but then isn't the acceleration not negative?
It's below the x-axis. Not that its slope is negative or positive.
Okay, yeah.
It's that it's below the x-axis. Yeah.
Cool.
So great. And how did you know that point was 2?
Oh,
It's where the acceleration is 0, right? If you solve that equal to 0, it is 2. So yes, you're right, 1 to 2. I just wanted to make sure you knew why. Are we okay with that one? Do we want to look at it again? Alexis?
Why is it 1 to 2 and not 1 to 3?
Because once we get past 2, the acceleration is now positive, right? Everybody's cool? Okay. Let's look for the next spots where the acceleration is positive, but the velocity is negative. So we'll start looking here, right? Because that's the first spot, the acceleration, it becomes positive. And there the velocity is negative, and it stays negative all the way to 3. So from 2 to 3. And then the last place we'll look for is the acceleration is negative, but the velocity is positive. So that happens here, is the last place that happens, right? From the beginning all the way to there. So 0 to 1. So if we were to put this together, or if we go back to our diagram, if yellow is, well, let's not do it that way. Let's have yellow or green be speeding up like a green light, and yellow slowing down like a yellow light. That makes more sense to color code them. So let's go back here and just kind of label this. I don't want to ride with you. I don't want to ride with you. I heard that. So what did we say? We said 1 to 2. So that would be here. And then after 3. And then we're slowing down from 0 to 1. And then from 1 to 2. So as we're leading into the stop, we're slowing down. And immediately after a stop, we should be speeding up. Right? Paul? Absolutely. What do you guys think on this? Again, calculus, pretty light, right? Algebra and context, a little bit heavier. That's going to be pretty on par for the next couple of sections, where the calculus pieces are going to be pretty doable, almost easy, like chapter 2 level calculus. All right. Let's look at another example. Come on, friend. There we go. Okay. Let's look at this one. This says if a rod or a piece of wire is homogeneous, what does homogeneous mean again? It's like the same throughout, right? Okay. Then its linear density is uniform and defined as mass per unit length. Great. And we measure that in kilograms per meter. Okay. Suppose, however, that the rod is not homogeneous, but that its mass is measured from its left end point to be f of x as shown in figure 5. So starting from the far left end of the rod, the length forward is a function of that length of rod. That's going to give you its mass. So it may be heavier at one end than the other, or maybe not even like increasing or decreasing consistently across, right? It could just be like all kinds of wackiness going on, whatever that function is. The mass of the part of the rod that lies between x1 and x2 is just going to be the change in mass. So f of x2 minus f of x1. Everybody agree with that? So the average density for that part of the rod is just going to be the change in m divided by the change in x. So f of x2 minus f of x1 divided by x2 minus x1. What's that look like? Slope.
Oh my God.
Right? All of these average whatevers, what are they? Slope. Okay. Now, if we let that change in x approach 0, that is, if x2 approaches the position of x1, we are computing the average density over smaller and smaller intervals. The linear density at x1 is the limit of these average densities. That is, the linear density is the rate of change of mass with respect to length. Symbolically, it is this guy. What does this look like the same as? The derivative, aka the instantaneous, in this case, since we're talking about density. Maybe I think we said linear density. So what are we seeing? The linear density of the rod is the derivative of mass with respect to length. Not a big deal. So, for instance, if the mass function is the square root of x, that's measured in meters and m is measured in kilograms, then the average density of the part of the rod given by 1 to 2 is how do we do the average linear density? It's the slope. So it's just going to be square root of x of 1.2 minus square root of 1 over 1.2 minus 1. If I go and I grind that on my calculator, I get 0.48. And this would be kilograms per meter, I think was the units we were using here. Now, what would our instantaneous linear density be? Well, we'll take the derivative with respect to x of both sides of our mass equation. What is the derivative with respect to m of, or with respect to x of m? dm dx, right? Just like an implicit differentiation problem. And the derivative with respect to x of the square root of x is? Okay, and if we evaluate that at the first point of our rod, what do we get? .5 kilograms per meter. What did you think? How was the calculus on that? Pretty easy, right? Just the question of like, what am I doing calculus on? is kind of the hard part, right? Okay. I'm going to skip ahead a couple. So this was a chemistry one. What do we got here? This is like a biology blood flow one. I'm going to go to the economics one. I know that several people have expressed interest in like calculus with regard to business. So let's skip to an economics problem. Sound good? I'm trying, guys. I know people have asked about it. All right. So it says, suppose C of X is the total cost that a company incurs in producing X units of a certain commodity. The function C is commonly called a cost function. If the number of items produced is increased from X1 to X2, then the additional cost, the delta C, is equal to C of X2 minus C of X1. And the average rate of change of cost is C of X1 plus that change in X minus C of X1 divided by the change in X. Everybody's okay with that? The limit of this quantity as delta X, the change in X, approaches 0, that is the instantaneous change of cost with respect to the number of items produced, is called the marginal cost by economists. So the marginal cost is basically the change in cost to produce one additional unit. So like the marginal cost at when X is 5,000 or whatever is like how much does it cost for one more unit to make the 5,000 in first unit of item, right? Because that cost is going to change depending on how many you're making. Most of the time that's not a constant, right? They have a little caveat here that says since X often takes on only integer values, like you can't make a third of an item or something, it may not make literal sense to let delta X approach 0, but we can replace C of X by a smooth approximating function as they did in example 6. Basically, instead of having like a stepped function that is only defined at points, you just smooth it out and we'll make an approximation. It'll be good enough. If we take delta X to equal 1 and n large enough so that that delta X is small in comparison to n, we get that the derivative of n, of the derivative cost, the value of the cost function evaluated at n, is approximately C of n plus 1 minus C of n. Where are they getting this from? It's the average, or we've just filled in delta X to be 1. That's all it is. So if that number of units produced is big enough, then the average marginal cost approximates the instantaneous marginal cost. That's all we're saying. Everybody's okay with that? Okay. Thus, the marginal cost of producing n units is approximately equal to the cost of producing one more additional unit. Is often appropriate to represent the total cost function by a polynomial, where A represents the overhead costs like rent, heat, maintenance, etc., and the other items represent cost of raw materials, labor, etc. Blah, 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 blah. Some details about like why that even makes sense. For instance, suppose that a company has estimated the total cost in dollars of producing X items to be C of X equals 10,000 plus 5X plus 0.01X squared. So the marginal cost function is the derivative, 5 plus 0.02X. And the marginal cost at the production level of 5,000 items then is the derivative evaluated at, I meant 500, at 500, which gives us $15 per item. If we compare that to the actual cost of producing the 501st item, we take the cost to make 501 items and subtract it from the cost for 500 items, we get $15.01 approximately. So what are we noticing? That marginal cost is a pretty good estimate, right? That's what we're seeing. Now, you can do these marginals with anything. You can study marginal demand or marginal revenue or marginal profit, which are just going to be the same idea. They're just the first derivatives of demand, profit, revenue, etc. And we'll do this again in chapter 4 when we talk about how to find maxes and mins for a function using calculus, because those will often be important in an economic standpoint, like where to maximize profit, like how many items should I produce to maximize profit? Feels like something good to know. Or minimize costs or maximize really revenue, depending on what you're trying to do with your business, whether it's want to get profit share if I just want raw income. You know what I mean? Anyways, that feels like you guys feel okay with what we're doing here? Really, the calculus part is easy, right? It's just going to be like the setup stuff. Yeah, and it's like most story problems, the core skill is reading comprehension, like just reading and understanding what's going on. So here we're going to ask you guys to do, I have this written down on the next page, it looks like. Okay. 1, 3, 5 through 7, 13, 15, 17, 26, 31, 33, 35. Again, next time we'll take questions on this and we'll talk about section 3.8, which is, again, more of these like application kind of ideas. And then we'll, ideally we'll also start 3.9 next time, which is a toughie. Not from a calculus standpoint, but these are some, the calculus parts usually aren't bad. It's the setup part that's the hard part in 3.9. But this is, 3.9 is, the topic is related rates. This is a classic, like, first year calculus, one of the harder things you do in first semester topic. Because the story problem nature is like, becomes kind of tough understanding, like, okay, what are the variables and not the variables? What is it that I'm really solving for? How do I like set this up in a way that when I differentiate, I get the things that I want as variables and not things that I don't want as variables? We'll talk more about it next time. Hopefully we'll get that far. We'll see. And that 3.9 section will be the subject of our homework quiz for this second half. We'll do that with partners in class or whatever. And we'll talk about like what you need to be able to do for your scores or whatever, but that's going to be a paper and pencil guy as opposed to online, since these are like free response level questions. Cool? Just to give you a taste of what's kind of coming. So that homework quiz probably won't be till Friday at the earliest, but probably not. We'll just see if we get through 3.9 on Wednesday. We'll see what it feels like is the best option there. Yeah, Joe. Of course.